Hello friends, so till now we were discussing I think quite few number of lectures on phase diagram, and then we looked at some phase transformation kind of ideas, and we looked at some heat treatment procedures. Okay. So now we will be shifting our course to mechanical properties. Okay. And before coming to mechanical properties, okay, or what do we call as mechanical response of material, okay, to any mechanical stress or strain. Okay. So, first thing we want to discuss in this is called elastic behavior. So, if you look at any material, okay, they will always show you some elastic behavior and some plastic behavior. So, first we will look at the elastic behavior, and then we will go further and look at plastic behavior. So, first we want to know that what do we mean by elastic behavior of the material. Okay. So, before that let us define few terms here. Okay. One is the normal stress. Okay. So, you can see that one sample is shown here, and we are showing you a cross sectional area here. Okay. So, this is, you can say, cross sectional area rather than just area, okay, which is given by A, and we are applying one force here on this material, which we are saying as F. Okay. So, what do we mean by stress? The stress will be defined as F force divided by area. So, force per unit area is the stress which is acting on this sample. Okay. And the unit for that will be Newton per meter square, okay, or which is also can be referred as Pascal. And since force is applied normal to the area here, the stress is called normal stress, and this can be either tensile. So, tensile means I am elongating the material, or it can be compressive in nature, in which case I am basically compressing the material, or I am shortening the length of the sample. Okay. So, it can be tensile where you are stretching it, and it can be compressive. Okay. And in both the cases, because I am applying the force normal to the area, then that is why it is called normal stress. There is another kind of stress can be possible, in which case we will call it as shear stress. So, now in this case force is applied parallel to the area. Okay. So, I am calling it as Fs now because it is parallel to the area. So, again this is my area is defined, and I am applying the force parallel to that. So, shear stress I am defining by a symbol here as tau, okay, which is again force per unit area, which will give you the shear stress. Okay. Again the units will be same as Newton per meter square or Pascal. Now, there is another term. Okay. So, stress can be there, and similarly there can be a strain. Okay. So, what do we mean by strain? Strain is basically change in length divided by initial length. Okay. Any change in the length divided by initial length is equal to strain. So, basically when you apply a force like this, okay, I have changed the length. So, initial length, let us say for my material was L, okay, and the change in length is, let us say, given by delta L. Okay. Then the strain will be change in length, which is delta L divided by the initial length, that will be equal to the normal strain. Again because I am measuring the strain on the area which is normal to the stress. Okay. So, I will call it as normal strain. Similarly, there can be shear strain, okay, which will be because of the force applied to the parallel to the area. So, suppose this is my initial object, okay, and I am applying a force here in this direction. Okay. So, because of that my material is deformed like this. Okay. So, let us say my height of this sample was h, and this deformation is, let us say, A, and this new edge is making an angle theta with the old edge. Okay. Then I can define the shear strain, which is I am referring here as gamma, that will be the displacement A divided by the perpendicular distance from the fixed end, which is h, a by h, and that will be obviously, because this is a perpendicular and this is the base, okay, perpendicular upon base, then and this is angle theta, so it will be equal to tan theta. So this is the shear strain, okay, because of the shear stress on the material, whatever strain is produced is called shear strain, and that will be equal to a by h equal to tan theta. Okay. So these are definition for stress and definition for strain. Okay. Very quick definitions we are doing here. For a very detailed definition of stress, I would suggest that as a mechanical engineer student, you must be going through a course called strength of materials. Okay. In that you will see a detailed definition of stress. We are not doing it here. Okay. For that you go through that particular course. Okay. Now what is elastic behavior? Okay. So once we have defined stress and strain, now we can look at elastic behavior of the material. It is the material, if material recovers its dimension after removal of load. Okay. So if I have applied a load, okay, and when I remove the load, it goes back to its original position. Okay. One of the very good example of understanding this type of behavior is you can see in springs. Okay. So you take a spring, you compress it, and when you leave the load, it will go back to its original position. Okay. For if I stretch it, okay, and when I remove the load, it will again go back to its original position. Okay. So spring is one example very close to this idea. Of course, there is no spring when we are talking about material. Okay. But the behavior is same, that when I apply the load, okay, it will deform. When I remove the load, it will come back to its original position. Why we are understanding of elastic behavior is important? It is important because most engineering design is done in the elastic region. As a mechanical engineer, whatever design you are going to do for any structure, okay, it has to be done under elastic limit. Okay. That means it has to be done where the material show elastic behavior. You cannot cross the yield or you cannot cross the limit where it starts deforming plastically. Okay. Because if it does deform plastically, that means it the material has failed. Okay. So in the strength of material approach, again that will come to understand as a yield criteria. So for any engineering design, it is important that your material should not cross the elastic behavior of region. Okay. Macroscopically, if you see, most polycrystalline material are elastically isotropic, so we do not have any problem of that they may show anisotropy. Microscopically, it can have anisotropy, but since materials, most of the engineering material are polycrystalline, I do not have to worry about that. Then there is another concept called viscoelastic properties of material, in which case this reversible deformation that occurs is dependent on time. If it is not a viscoelastic, okay, normal elastic behavior, then as soon as I leave the load, it will go back to its original position, okay, without any time delay. Okay. But if there is any time delay involved in this, okay, and as I told you earlier also, that any time factor when it comes, it is called visco, is a prefix is added. So if the reversible deformation is time dependent, it takes some time to go back to its original position, then that is called viscoelastic behavior. So this is how elastic behavior will look like in a typical stress strain curve. Okay. So you have stress on the y axis and strain on the x axis. Please remember, when we show something like this, we are showing it in, because when we do a tensile test, okay, what we impose on the material is strain, not the stress. Okay. We force the material to deform, and the stress is the response of the material to this elongation or strain. Okay. In normal practice, basically we apply the load and the material response is in form of strain. Okay. So there can be different situation in different cases, but when we do a tensile test, okay, what we are imposing or what is the independent variable is strain. I am deforming, my cross head of the machine is moving and it is deforming the material, it is imposing a strain, okay, and material is responding in form of stress, okay, and that is what is measured using load cell in the machine, okay, and that is what is reported. Okay. So, basically on the x axis it can be elongation, okay, movement of the cross head, or you can convert that into strain because delta L by L. It will also give you force, okay, from the machine, that can be converted to stress. So, force divided by initial area, that will give stress, and the elastic, in the elastic part it will have this linear behavior between strain and stress. So, stress is linearly dependent on strain, okay, and the slope of this linear curve is what we call as elastic modulus or Young's modulus, E, okay. So, slope of the curve will give you E, and this linear dependence of stress on strain, which is what we call as Hooke's law, stress is proportional to strain. So, sigma is equal to E into strain, okay, that is what is Hooke's law. What it measures elastic modulus or Young's modulus, measures the resistance of a material to elastic deformation, as I told you that whatever deformation I am imposing, its resistance. So, if you have high elastic modulus, that means resistance will be more, you will require more stress. So, if a material has low elastic modulus, it will be, slope will be small. If material has very high elastic modulus, the slope will be high. So, resistance will be high for the same amount of deformation, okay. In this case the stress is this much, in this case the stress is this much, resistance has increased. So, it gives you a resistance to deformation, okay, and it is the response of the material in form of stress when you are imposing strain. In case of shear strain also you can do same thing. Similarly, shear strain is proportional to shear stress. So, shear stress is proportional to shear strain. So, I will just do some small correction here. So, that tau is equal to G gamma, okay. So, here you are getting a new elastic modulus, okay, a new elastic constant, which is the shear modulus or modulus of rigidity. So, when I am doing under shear condition, then I am going to use the shear modulus. When I am doing in a tensile, uniaxial tensile or compressive type of experiment, then I will be relating the stress with the strain using Young's modulus. So, what type of deformation I am doing, I have to choose elastic constant accordingly. So, this is the spring analogy for elastic deformation, as I told you, okay, that you have atoms, okay, and atoms are basically having bonds between them, okay, and then bonds can be considered as spring, okay. So, when I am deforming it, the spring is getting stretched. So, as soon as I remove the force, it will go back to its original position, okay. So, removal of force will bring spring to initial dimension. So, I can use a spring analogy to explain this, that a solid is made of hard sphere which are atom and connected by spring which are interatomic forces or potential, okay, and as soon as I remove the force, it will go back to its original position, okay. So, basically if you look at elastic behavior, applied force is transmitted by the network of bonds constituting the material. So, of course, there are bonds between the atoms. The elastic behavior depends quantitatively on the magnitude of the interatomic forces. So, if you have a stronger bond, okay, then you will require more force to deform it, okay. That means the elastic Young's modulus of that material will be high. So, if stronger bonds are there, elastic modulus will be high, Young's modulus will be high. More interatomic forces, you have more bond strength, more Young's modulus. Elastic properties do not depend on microstructure of the material. This is very important to note, that my Young's modulus does not depend on the microstructure of the material. So, you can have fine grain, you can have coarse grain, whatever. It is not going to depend on the microstructure, the elastic modulus, okay. It is only dependent on the bond strength, and that is not changing. So, bond forms when atom either share, example it can be covalent or metallic bonds, or it can be ionic bonds. Okay. So, depending upon different type of bonds, you will have different bond strength and different elastic modulus. Of course, the bond strength, length should be such that it is minimizing the potential energy for the system. Okay. So, let me just bring this aspect out. If you see in terms of potential energy, okay, the curve for potential energy is something like this. Okay. This is the distance okay. So, it will be something like this. This is the position where you are going to have minimum energy. Okay. So, this will be the bond length. So, distance between atoms. Okay. So, this is the distance, equilibrium distance. If I bring them closer, the potential energy will increase. If I take them apart, again the potential energy will increase. Okay. So, whether I do stretching or whether I bring them closer, in both the cases the potential energy will increase. Okay. And that is what we do not want, and that is what atoms do not want. Okay. So, as soon as I remove the force, it will try to go back to its minimum potential energy configuration, which is what is the equilibrium distance between the atoms. Okay. So, this is what is the driving force for elastic deformation. These are some values of Young's modulus of different material type. Okay. So, you can see that covalent or ionic bonds are very strong bonds, so very high elastic modulus. Okay. And this is for metallic bonds. Steel has very high long elastic modulus than copper, aluminum, zinc, depending upon their bond strength. Okay. They will be grouped in different categories here. Some for polymers also are shown here, polymer and composite. Now, after understanding the elastic deformation and Young's modulus, there is another very important parameter when you are doing deformation under elastic limit, is called Poisson's ratio. Okay. What does it mean? That when I am applying a tensile stress, for example, in z axis, okay, in this direction. So, when I am elongating in z direction, there has to be contraction in the x and y direction. Okay. So, that is what is there. So, when I am doing a stretching along z axis, there has to be contraction along the x and y axis. The lateral strain, lateral means this two in x and y direction, is a constant fraction of strain in the longitudinal direction, that is in the z direction, and that is known as Poisson's ratio. So, suppose this is a cube, okay, as shown here, okay, and I want to apply a force here in z axis, and because of that it will deform, elongate in z direction, and there will be contraction in x and y direction. Okay. So, if you measure all these dimensions, okay, the strain in the x or y direction divided by the strain in the z direction will give you the Poisson's ratio. So, Poisson's ratio nu is equal to lateral strain about longitudinal strain. Okay. So, epsilon x in the x direction or epsilon y in the y direction is equal to minus nu of epsilon z. Okay. Why we are keeping minus sign here is because if a strain in the z direction is tensile, the strain in x and y direction is, there is a contraction, okay, there is a negative dilation. Okay. So, that is why we are using minus here, okay, that epsilon s will be equal to minus of nu into epsilon z, okay, or epsilon y is equal to minus of nu into epsilon z. Okay. So, if one is tensile, other has to be compressive, and that is why the negative sign. Now, there is another concept called elastic strain energy. As you can see that when I am deforming it, my potential energy is increasing. That means I am storing the strain energy in the material, in of course elastic strain energy in this case, because we are doing it under elastic limit. So, elastic deformation is stored as elastic strain energy in the material, okay. And how, what do we mean by energy? Energy is equal to force into distance. So, during elastic deformation it is area under the load deformation curve. So, if I instead of plotting stress versus strain, if I plot deformation versus load, area under the curve, okay, and area under the curve will be equal to half of force into displacement, okay, and that will give me the area under the curve. So, this is my elastic strain energy which is stored in the material when I am deforming it, and when I release the force, okay, this strain energy will be recovered, okay, and of course, this energy has to go somewhere. Actually it will go in heating the material, okay. So, if I keep on doing suppose this continuously, after some time you will see that the material is heated up, okay, because this strain energy which is stored will be dissipated in form of heat, and slowly you will see that the temperature of your material is rising if you keep doing this for quite number of time, okay. So, with this we have covered the elastic part of the deformation, okay, very important for a mechanical engineer, and of course, you have a kind of a full course on that in terms of strength of materials course, okay, where the whole treatment is under elastic limit, and actually you understand the whole elastic deformation in much detail than what we did here. Okay, here we are just kind of trying to understand that when you do a stress strain deformation or you plot a stress strain curve, there has to be some elastic region and then there has to be some plastic region, okay. In elastic region you can have certain things which we try to understand in the present lecture. So, thank you very much.